All right, let's go back here. So waves undergo four things, right? Waves undergo reflection, right? So if you look here, we have a reflected wave, right? If you look here, what we have is a reflected wave, right? Right, the reflected wave is the three most important things. We'll talk about all this now. In a reflected wave, you'll recognize that the angle of incidence and the angle of reflection are equal. Okay, now? Then the next phenomenon is refraction. Look at that ray of light there. Look at the ray of light that leaving the fish. What happened to the ray of light? It didn't stay straight, right? It went, right? So refraction is depending of light. All okay, right? Right? So that's phenomenon number 2. That is called the refraction of light. Number 3, if we look here at number 3 is diffraction of light. What do you reckon has happened to the light there? As the light went through, what happened? Kind of spread out. You see that? So it went through a straight line, and when it came through the opening, it kind of spread out a little bit. Okay? So that is phenomenon number 3. And phenomenon number 4 is interference, right? What you will notice here, these two waves, when they meet, they form in a larger wave. Here, when those two waves meet, it cancels out. Anybody remember what you called those two waves? They are said to be what? What's that? Outer phase. Very good. And these two here are what? In phase. Nice. Okay? And basically, here's an example of interference. Right? When light interferes, it produces light and dark patterns. Okay? All right. So, head up wave phenomena. And I want you now in your own words to write down the 4 things and what you think they represent. The 4 wave phenomena. In your own words, what do you think each one is? Try that, please. Online. Try that, please.
Yeah, but only TV.
Right? In your own words, write down the 4 wave phenomena and what do you think each one represents? Right, let's see how much fate got. Fate has reflection, refraction, diffraction, interference. Okay. So those are your four-wave phenomena. Right, so write down the four-wave phenomena again. Reflection, that's number one. Number two, refraction. Number three, diffraction. Diffraction. And number four, interference. Right? So we're going after the first one, reflection. Right? Let's write a small note on reflection. So let's say this. Reflection of light. Right? Online, draw that please. And I'm going to show you a simulation of how it moves, right? This one is No class Monday. No class Monday. Say that right? Monday. I'll give them Monday off. Right. When they write it, you'll recognize that the main feature of reflection is what? What's the main feature of reflection? The angle of incidence equal to the angle of reflection, right? So if you watch here, let's say we have a plane surface and we have an incident ray, right? That arrow represents an incident ray. If we have an incident ray, when the incident ray touches the surface, 90 degrees at that point is what you call your normal. Right? And how do you measure your angles? From your ray to your normal. That is called the angle of incidence. Okay? And the special property about reflection is that that angle is equal to the angle of reflection. Right? So I is equal to R all the time. Okay? That's a special property of reflection, right? That's what you would have seen in the handout. Right? But there's two quick things I want to write down. Two quick things I want you to note. Number one, we always measure our angles. Let's make a note of that, please. We always measure our angles between the normal and the ray. We always measure our angles between the normal and the ray. So whenever you're measuring the angles, please remember you're always using here. Between the ray and the normal. Okay? Normal and the ray. And number two, the normal is an imaginary line. Degrees to the surface. Normal is an imaginary line. 90 degrees to the surface. Normal is an imaginary line. 90 degrees to the surface. At point of incidence. At the point of incidence. All right, look at diagram 1, right? Look at diagram A. Where is the normal? Watch this here. Have a ray and the ray coming in here. Where is the normal? It will be vertical, right? So at that point of incidence, 90 degrees. That's okay? That line there is your normal. All okay with that? Right, but here now. Where is the normal? Want to draw it? Anybody online could draw? Caleb? Maria? You could draw that?
So I think we could draw it. Also.
Right now, try and draw a normal left one. Remember it's an imaginary line, so have to be a one line, right?
$90 degrees. So it could be here.
Nice. Second word, Caleb. Very good. You're saying that? There is the point of incident. 90 degrees there. Good job. Right, it's important that I get draw this, right? Try one more now, please. Right, draw ABC in your book and draw the angle left. ABC, draw a normal. Ready? Right, so at that point, 90 degrees to that point. Okay? Right, at the point, just measure 90 degrees. At that point, and enjoy a broken line. Right, let's go again. Okay, nice. Right, let's move on. And here we have our two laws of reflection. The first law of reflection, incident ray, normal ray, and the reflected ray lie on the same plane, right? And the next angle of incident equal to the angle of reflection, right? If you consider a plane as a piece of paper, right? Every ray is on that piece of paper. Normal, the incident, and the reflected. So they all lie on that same piece of paper. And the second law is the angle of incidence equals to the angle of reflection. Okay, now good. So we know the laws, right? We know the laws. Let's check out this simulation here quickly. Right? A nice little simulation here. This one is push-ups. I delete it already, right? Delete it already. So based on the load content, right? Based on the full flexion, right? Here, flexibility, right? We look here what we have some flexibility, right? What going on is most important thing to all just now. In a reflective way, you'll recognize that the angle incidence and the angle reflection. Okay, now. Then next phenomenon is look at that real light here. Look at the real light. It's practically real light. Who play that? Somebody play that? Don't you hear me now? Well, you live me? Are they recorded?
Yeah.
All right, sorry there. Right. What you was asking that Caleb?
So you cut off the states too quick.
Yeah, I'm sure tell you which law you missing. First or the second law.
The second one.
Right? The second law is the angle of incidence equal to the angle of reflection.
Okay.
All right. I want to show you all a quick little simulation so you have an idea what's going on. Huh? All right, hold on. I normally use just a refraction, but let's just see. Right. All right. Forget the way underneath for now, right? Forget the way underneath for now. If you look here, right. Right. Hold on. Right. This is it. Right. You'll see that online. So look at this ray. When this ray from the torchlight hits the surface, you'll recognize. I'm not sure if you'll see it there, but the angle of incidence equal to the angle of reflection. Okay, that's on a nice smooth surface, right? If I were to adjust it slightly, right? If I were to adjust it slightly, same thing. Angle of incidence equal to the angle of reflection, right? So it doesn't really matter where I adjust it. angle of incidence equal to angle of reflection. That's okay? That's the principles of reflection. Are we okay with that? So once an object or once a ray of light undergoes reflection, incident angle equal to the reflection angle. That's it. All right. Let's move now to the refraction. Right. Look at this ray of light here. If you look at this ray of light, you'll recognize that this ray of light that will exit there, it is going across two medium. The white medium is air, and the blue medium is water. If we play it, what will happen? You'll recognize that this ray of light was initially traveling along this angle here, and instead of going straight through or reflecting, it bends closer to the normal. You've seen that? So I want you to show you as well that the angle, as it went from here to here, the angle got smaller. All right, let's see if this will work. What's the angle here, right? Let's make the angle a little more readable. 50 degrees. You'll see that? The angle here, that's the angle of incidence of 30. So instead of the ray continuing a straight line, what the ray did is that the ray bent inwards a little bit. It bent inwards to about the angle of what's it looking like there? I would say 10, 20, 23 or something. Kind of in the middle. So it went from 30 degrees to 23 degrees. So what it showed there, Faith, it showed some bending there. It showed that the ray, it didn't stay in a straight line, it bent towards the normal. Okay? And the reason for that, this simulation is given speed. Let's see if we can get the intensity of the wave. Look at what happens to the wave here. You all recognize it's not as intense. Its full intensity is 100% here, but when it's lower inside, the intensity is a little bit lower. Here's what happened. The wave slowed down. Right? As the wave entered the water, it slowed down. So in slowing down, it came a little bit closer to the normal. You see that? Let's just say I change in water, and instead of water, I put it in glass. What do you all think will happen to the refracted ray? So instead of water, I'm going to put glass. What do you all expect to happen? Any guess? Would it slow down more? Would it slow down less? Would it move away from the normal? Do what? Slow down more. So it will go closer to the normal. What you all think online? Adele? Quinn? What you all think? Carlo, what do you think? If I change the water to glass, what do you think will happen? Huh? Bounce back. Good try. Malini, what do you think will happen? Can I move towards the normal more or away? Away? All right. Let's see. Online, what do you all think? Kaya? Maria? What you all think might happen?
So I think it might slow down less.
It might slow down less. Okay, good try. Jaya, further away from the normal. Okay, I have two answers. Both say kind of further away. Well, let's see. Let us see. Mobile glass there, right? Let's check back the angle. Initially, it was 30, right? What it looking like now? So, well, in case you're not seeing it, all right, the angle was 30 degrees, and now this angle here a little bit smaller. It's about 10, it's almost about 20 degrees. So glass slowing down even more. You all realize that? Glass slowing down even more. What's going to happen here now? I'm going to move it further away from glass to something down here. What I'm going to do? Watch it here. As I move from air and I go to water, watch how the ray behaving, the refraction rate. Online it might be right here like diamond or something. What happened to the refracted rate? The refracted rate slowing down more and it's going closer and closer to the normal. Why any phone can shop? Taking time. Alright, good. Tell me what? But surely go ahead. Lock it off for that, please. That's not fair. Just what you've read, read. Otherwise, it's too much. Right, so as you move away from glass and it goes to something more what is changing there? Anybody recognize? So watch it again. As we go from air, we go into water, we go into glass, then we go into something more dense, maybe diamond. Right? What happened in there? Huh? Right, very good. Again, denser. So the more dense it is, the greater the greater credit. That's okay? Take up. One line. That's okay there? Katrina? Sahara? Are you okay there?
Yes,
so
sir.
Right. So the more dense it is, the greater the refraction. Okay, nice. Anybody can explain why this happened? A to A. A to A. What happened there? Same density, so therefore, right? No refraction, right? Same density. Nice. I want to do some small calculations here, but I'm not sure if let me try it. Wait. Look at glass. Look at glass there. Just do me a favor now. Find sine of this value divided by sine of this value. Let me watch again. Right close to them on the calculator. Once you get 1 point, write it from the top now. 1.5. Sorry. 1.5, right? Just check this again. I'm going to change the angle a little bit here. I'm going to go from 30. Let's move the angle to something that we can read. Let's say, what's that? 50. Right, 50. Here is 50, and here is 31 minutes. Can you open up for me, please? Sine 50 over sine 31. How much you get? About 1.5 again? 1.5 again. Just check one more for me, please. One more. $60. When it's 60, when I is 60, will be about 30. Let me say 35-ish. 35-ish. Sine 60 over sine 1.5. 1.51. Nice. What do you recognize there earlier? What do you recognize it? Anybody? Keep getting 1.5. Keep getting 1.5. What do you recognize? Same one. Same amount of refraction, right? So we call that refractive index. So exactly what we did there, a guy named Snell did the same thing. Snell, and Snell recognized that the refractive index remained the same. Every time he divides sine I by sine R, he keeps getting the same value. So we call that the refractive index. Okay? Are you okay with that? Yeah? You may have done this in French too, right? Yeah. All material, same ratio. Not the same value though. Right? Same ratio. Okay, so Snell was able to put that together, right? Online, Adele, are you okay there? Sahara? Bailey? All right, so let's go into the node part. I'm going to show you one more thing. What is here? Why did I keep happening? But I saw somebody else. Right. Watch this here, right? And we'll talk about this later on in class. What shall I read it? You want that ray? That ray is not entering anything. Is that ray being refracted at all? No. That ray is not being refracted. So once you have a ray, you have to imagine the normal in your head. Where is the normal for that ray? Huh? Where, no, that can't be the normal. Normal is what? Gotta be careful. Where's the normal there? Actually, they use it. All right, so watch it here. Let's use their normal. Right? So once a ray traveling along the normal, nothing happens there. It's undeviated. But watch this here, right? Can I switch? Oh no. I can't switch it. Let's put water on top. And let's put air. Right. Watch this cool thing here, right? You all see refraction right now? Yeah? How about now? You see that there? Watch this here. See what happened there? Refracted will disappear. So what happening now as the angle gets bigger? What is called that there? Huh? Reflection, very good. Right? Reflection happening there, Jacob. You see that? So something happening there, and I will explain that phenomenon in a little while. Everybody okay with that? And that what you're experiencing there is called total internal reflection. Okay? Refraction not happening anymore. Only reflection. All right, nice. Let's go back to the notes, and we can jump into past papers very soon. You didn't do any past papers yet, sir? Oh, they're excited for past papers. I'll tell you what, you know. What's enough? Future, right? right color. So you may call it right color this for that refractive index. And then we're gonna try some questions on it. Wait, I didn't send all of this document. I can just send all of this. You'll got to rewrite all of this. Okay, I'll send it. Right? But I want you to, I will send the document so you don't have to write all of this, right? But I want you to write this part here from refractive index. Right? Maybe the table underneath. Right? The refractive index part there. One times. Apply on fast. No, no.
I don't have a question.
More dense is fluid. And the more dense it bends towards the normal. More dense bends towards the normal. Look at it. Right? So the more dense the slower it will move, right? Most important thing is write down the formulas here, right? Right, here's a quick calculation. Anybody write this down? Anybody write it? Please remember your symbols, right? Right, remember wavelength. Remember your symbol for wavelength, right? So now we reach the calculation part of waves. Right, if you look here, now watch it. What do we reach? Also right side. Anybody never did waves before in school? Anybody never did waves in school? So the good thing is you would have covered all topics already. That's perfect. Nice. Yeah, they were. All right. A small example here. Example 1. Calculate the refractive index of light passing from medium A to medium B. Right? Watch this closely here. How do we find refractive index? Right? We have angles, so we're using the angle version of the formula. Sine I over sine R. Right? If you look closely there, well, what is the angle of incidence? 45. You always measure the angle where? Between the normal and the ray. So right here, right? Always between normal and the ray, right here. So the angle is 45. So that'll be sine 45. What's the angle of refraction? 60. Because it's between the normal and the ray. So that is tricky, right? So it's sine 45 over sine 60. How much is that? With the calculator. Or the arrow going up. Okay, now change it. I go it down. Thanks, Sam. Thanks, Daria. I go it down. I go it from medium B to medium A. How much? 0.8. 0.8. Anybody have that? 0.8? Yeah? Yeah? 0.8? So, what does that 0.8 tell us? That's the refractive index of what? Look at the arrow, go from B to A. What does that 0.8 tell us? Big number. What does that 0.8 tell us? It's the refractive index of what? Of right? So it's the refractive index, but look at where the ray going. The ray going from B into A. So it's the refractive index of A with respect to B. Okay? So if you have to say it, that's the refractive index of A with respect to B. Because if I were to change medium B and leave medium A, its value here will change. Okay? So that 0.8 represents the refractive index of medium A with respect to medium B. You see that? Yeah? Let's go the other way around now. Make a note of that, please. Make a note of that. The ray is going from B to A. So what we found is the refractive index of A with respect to B. Right? So that diagram is showing us the refractive index of A. Look at the ray. The ray going towards A. So A doing the refracting, right? So what we found there is the refractive index of A with respect to what it came from, which is B. Okay? So that's the refractive index of A with respect to B. What about if we flip it around? Are you all right? Sir? What about if we flip this around now? Pardon me? What? Yeah, 45. I just want to flip it around, right? If I flip it around like this, the way going from A to B. Find the refractive index for me here. Find the refractive index for me here and tell me what you get. And label it properly. Label it properly. Put the other way around. Or some you will write it, sir. Just write it, sir. Right, notice the arrow going to change, right? Right? Can I take it off now? Take it off now. Right, work it out the next way from now. The ray is going from medium A to medium B. Work out the refractive index there from the place and label it properly. And label it properly, right? How much you got? 1 decimal place. Nah, I think 1 decimal place to do. 1 or 2 decimal. 60 divided by sin 60 divided by sin 45. No, going up, going up. Medium A to medium B. Right, just about the how much you got online? From medium A to medium B now. That'll be sine 60 over sine 45, right? How much you got online there? Online, any answers? Quinn, correct, Quinn. Barrage, how much you got? So the refractive index is 1.22. But how do we write it? It's the refractive index of what? Of medium B with respect to medium E. Okay? The refractive index of medium B with respect to E. Anybody can tell me how they relate it? Anybody can tell me how these two related? One was 1.22, I next to what? 0.9? Or 0.8? 0.8? How are these two related? Anybody? How are these two values related? Yeah? Over here? That's not the same formula. Sure? Anybody? Anybody online? Anywhere? Anywhere. How are these two related? I want to guess. You get right, class 1 finished now. How are these two related? Close, but I want to know specifically. How is this related to this? Alright, next. Anybody online? Anything? Katrina? Any guess there? Kaya? Jaden? Yeah? Close, you're getting closer. But those two things are related in a particular way. All right, then let me see if this might help. 1.22 is approximately 514, approximately. And this is 4 and 5. Inverted, right? Think about it. And the angle of incidence in one was the angle of refraction in next one. So they inverted. So sorry. So the refractive index of A with respect to B is 1 over the refractive index of B with respect to E. Right? So they inverted. Just flip it over. Right? And you'll get it. So that symbol there means inverted. Yeah. Yeah. Just if they ask to find the other way, they just put the answer over. And you can explain why. Yeah. Okay, so it's important I understand that these two things are included, right? Right. Normally I will give you a question. Right, but before we do that, if you were to plot a graph, if you were to plot a graph of sine I versus sine R, right, the gradient will give you what? Refractive index. Okay? So the gradient, you all may do this lab, right? You all may do this lab online, right? You all may do this lab in school. Sine I versus sine R is equal to refractive index. So they will give you a glass block and you have to find I and R values. Sign it and then find the gradient. Okay? All right. Before we go anywhere and start any papers, we have to understand something called critical angles. Right? And I showed you this in a simulation. So, critical angle is a special angle of incidence. Watch it here. Watch the diagram here. Right? Critical angle is a special angle of incidence that gives you an angle of refraction of 90 degrees. All right? Felicia, you're watching here? Right? So there is a special angle of incidence that will give you an angle of refraction of 90 degrees. And that special angle is called your critical angle. Right? And if by chance you were to go greater than this angle, you will end up with the phenomena I showed you all called total internal reflection. But you have to go beyond this angle. It has to be larger. You see that? Yeah? So what is critical angle? A special angle of incidence that gives you an angle of refraction of what? Of 90 degrees, right? What happens if you go greater than the critical angle? Total internal reflection. Okay with that? Yeah. And yes, and here's an example of where total internal reflection happens. Like in this fiber optics here. In this fiber optics, if you had a light ray, like a digital ray, it's constantly totally internally reflected. So it's not coming out of the medium. It's just reflecting and staying inside the medium. Okay? Right, last thing. Write the part in red and draw these 3 diagrams here. Huh? And then we can put that cluster. All right, so today we learned about reflection, refraction, total internal reflection, and critical angle, right? So that's past there. So, yeah. Huh? That's great. Yeah.
Let's just see.
What?
Let's say the move up and the tile underneath the pool looks so when it jumped in, it's
That's refraction. Sebastian, you okay there? Right, I'm gonna add these names here and you also include, right? Right, so I'll send you all these notes so you'll have them as well. Any questions online? So how you would describe total internal reflection? How you would describe that? Huh? Well, the subject at the highlighter. What is total listening? Total internal reflection. Right, exactly. That's when a ray is totally reflected inside itself. Okay. All right. You'll have you don't need past papers. I'll just use the soft copies, right? Next day we'll start looking at past papers. Right. So in this simulation, you would have seen the same thing. As the angle of incidence got larger, total internal reflection happens. I have to set this. Just show by hands again, not in the group. Please.
So me, so I'm not on the group.
11.
Yeah. So I ain't got no notes as yet.
Yeah, that's it.
Some main number that they need to add. To think of your number. And who? Tyrese.
Then it goes to
Okay, let me get into it. Right, somebody have WhatsApp now already because some of your public message if I forget. There's some man that's now idea. Yeah, who else here? What's the name again? Dario, you know that?
so it's Denico.
Cynico. So now what's up, right? Cynico. Really? I have a number now.
So, that's really how it's.
Sylvia and Piotr. You done?
Yes, sir. The number is 367
Yes, this Cynico have it there.
All right.
We not done?
Yeah, we are.
All right, yeah. I'll take it number. I'll take it number from my there.
Up to you, right, man, right?
Yeah, just give me a number, right? Cynico.
Yeah.
Yeah, but that's
Call it out.
I don't mind. You can log out, right?